What's up, guys? My name is IBM, and today I'm taking you through dynamics. This is going to be lesson 3. Do not forget, in dynamics, we basically concentrate on Newton's laws of motion and linear momentum. Those are the most important concepts to understand from dynamics. Do not forget to watch the solved past paper questions to gain as much confidence as possible. The solved past paper questions are both in multiple choice and also in short structured, so you can always check out my playlists for both the multiple choice in solved, the multiple choice solved past paper questions and um, the structured solved past paper questions. Okay, so today I want us to concentrate on linear momentum. Of course, there is a blend between linear momentum and Newton's laws of motion. We can't study linear momentum independent of the Newton's laws of motion, so they will still come in as we saw them in the previous lessons. Okay, so let's talk about linear momentum. Why is it called linear? Because in this case, we consider motion in a straight line. Of course, there's also what they call angular momentum, but we don't talk about angular momentum at this level. So in IGCSE, you define momentum, and it's still the same momentum we are talking about even at this level. So the linear momentum of a body is defined as the product of the body's mass and its velocity. That is mass times velocity. The same definition you gave in IGCSE. So momentum is basically mass times velocity. That is linear momentum, product of mass and velocity. Of course, this would be different from angular momentum, but like I said, we shall not talk about angular momentum at this level. So we shall use the symbol P, small letter P for momentum, and of course mv for mass and velocity. So you must have noticed from your IGCSE concepts that the magnitude, that momentum is a vector quantity which has magnitude and direction. So momentum has magnitude, that is an amount, because it depends on the mass of the object. So it has a magnitude, which is a size, that is a number which has a unit. However, momentum is a vector quantity, it has even direction, and the direction of the momentum cannot depend on the mass because mass has no direction. But the direction of momentum depends on the direction of the velocity. In other words, the momentum of of a body is in the same direction as the velocity or as the resultant velocity on the body. So momentum is a vector quantity as you described in IGCSE. Then the SI units of momentum, I think the SI units of momentum, you mentioned them to be kilogram, meters per second, because mass is measured in kilograms and velocity is measured in meters per second. So the momentum was kilogram meter per second. So since the mass of a body is constant, the momentum of a body is directly proportional to its velocity because the velocity can easily be changed rather than changing the mass of an object. So momentum is directly proportional to the velocity. But of course, if it is possible to change the mass, then we can also say momentum is directly proportional to the mass if the velocity is constant. Before we go into the details of momentum, let's first relate momentum to Newton's laws. We should now restate Newton's laws in terms of momentum. Remember the first law, which states that a body at rest will continue to be at rest and a body in motion would continue to move in a straight line with uniform velocity provided no resultant force acts on it. That was Newton's first law of motion. But since a body at rest has zero momentum because momentum depends on the velocity, that means a body at rest, its velocity is zero, so the momentum would be zero. A body moving with a uniform velocity, its velocity is constant, so the momentum will be constant. Therefore, we can restate Newton's first law in terms of momentum by saying that if a body is at rest, its momentum would remain zero, and if a body is moving with uniform velocity, its momentum would remain constant, provided no external resultant force acts on the body. That would be Newton's first law in terms of momentum. So the examiner may ask you to state Newton's first law or Newton's laws in terms of momentum. So we are going to state Newton's laws in terms of momentum. So the first law The first law in terms of momentum will therefore be stated as the momentum of a body remains constant unless an external resultant force acts on the body. So if no resultant external force acts on the body, we know that if the body is at rest, it would remain at rest. Its velocity will remain constant and zero. If a body is moving in a straight line, with a uniform velocity, its momentum will still remain constant because the velocity is constant. So the momentum of a body remains constant unless an external resultant force acts on the body. So that is Newton's first law in terms of momentum. That is Newton's first law in terms of momentum. The momentum of a body would remain constant unless acted upon or unless an external resultant force acts on the body. So if a body maintains its uniform velocity, its momentum is not changed. And if it remains at rest, again, its momentum zero does not change. Its momentum remains zero and does not change. That is Newton's first law in terms of momentum. Remember, the original law was a body at rest would remain at rest, and a body moving with uniform velocity in a straight line would continue moving with its uniform velocity, provided there is no external resultant force acting on the body. So that is Newton's first law. Let us also talk about the second law. Newton's second law expressed in terms of momentum. So remember, the second law stated that if the mass is constant, force was directly proportional to the acceleration. That is, the net force was directly proportional to the acceleration. The acceleration and the net force were acting in the same direction. Or we simply say that the rate of change, because force is the rate of change of momentum, so Newton's second law was Newton's second law was easily stated in terms of momentum because net force is the rate of change of momentum. So the rate of change of momentum was directly proportional to the net force, and it acts in the direction of the net force. That was Newton's second law in terms of momentum. The rate of change of momentum is directly proportional to the net force or resultant force, and acts in the direction of the net force. So here you must be talking about the net force, and I said every time you say F is equal to ma, F is the resultant force or it is the net force. So suppose a force F acts on a body of mass m for say a time t and causes its initial velocity u to change to the final velocity v. The momentum changes uniformly so the initial momentum is mu, that is m times u, and the final momentum is going to be m times v, of course in the time delta t. So it means force is the rate of change of momentum, so it is going to be the final momentum mv minus mu over t. When you factor out m, you get m into v minus u over t, and we know that the change in velocity over time is the acceleration. Therefore, a is going to be v minus u over t, and thus it means that F, which is actually the net force, is therefore simply going to be equal to ma. And I said every time you use F equals to ma, just note that F is the resultant force. F is strictly the resultant force acting on the body, or the net force acting on the body. But then if you cross multiply, you multiply t both sides of this equation here. If force equals the rate of change of momentum, then you cross multiply both sides. You have that F times t is equal to the change in momentum. And the change in momentum is going to be called the impulse. So impulse is therefore going to be equal to the change in momentum, which is the same as the product of force and time. That F is the net force. So impulse is the change in momentum, or impulse is the product of force and time. Impulse is the product of force and time, or impulse is equal to the change in momentum. And finally, I don't want you to forget that force will always be defined as the rate of change of momentum. At this level, I don't expect you to define force as a push or pull. You can't define force as a push or pull at your level. So force is the rate of change of momentum. Impulse is the product of force and time. Of course, you will notice that the units of impulse will be the same as the units of momentum. That means if impulse is force times time, and change in momentum will still have units as kilogram, meters per second, because momentum is mass times velocity. But yet F times T is also newtons times seconds. So it appears as if the units 1 newton second is the same as 1 kilogram meter per second. So many times the units of momentum could be newton seconds, they could be kilogram meters per second. So impulse, because impulse is a change in momentum, impulse is a vector quantity because it is simply a change in momentum, and we have already said that momentum is a vector quantity. Okay, let us also talk about Newton's third law in terms of momentum. Newton's third law in terms of momentum. Remember, the Newton's third law was that if you have two bodies in contact, body A was exerting a force on body B, and body B would exert an equal and opposite force on body A. So remember, force is the rate of change of momentum. So if body A exerts a force on body B, and body B exerts a force, an equal but opposite force on body A, remember the time of contact for the two bodies is the same. Therefore, we can say that the rate of change of momentum of body A due to body B, or the rate of change of momentum of body A due to the force by body B, is equal and opposite the rate of change of momentum of body B due to the force by body A, because force is the rate of change of momentum. So Newton's third law could be stated as the rate of change of momentum of body A due to the force by body B is equal and opposite to the rate of change of momentum of body B due to the force by body A. We are just modifying Newton's third law of motion, which was stating that the force on body B by body A is equal but opposite the force on body B on body A by body B. And since force is the rate of change of momentum, then instead of saying force, I'll just say the rate of change of momentum of body A due to the force by body B is equal and opposite the rate of change of momentum of body B due to the force by body A. That is Newton's third law in terms of momentum. So to understand this mathematically, maybe let's talk about this in terms of letters, or in terms of equations. So to understand this in more details, by Newton's third law, we said the force on body A is equal but opposite to the force on body B, which could be represented by this equation here. The minus showing that the two forces are in opposite directions. But remember, force is the rate of change of momentum. Force is the rate of change of momentum. That means now, where there is Fa, I'll put the rate of change in momentum for body A. So this is going to be the rate of change of momentum for body A should be equal to the rate of change of momentum for body B, but these are in opposite directions because force is the rate of change of momentum. Remember, the time of contact is the same. Therefore, the time for A, delta TA, is the same as delta TB. So the forces are in contact for the same time. The forces act on each body for the same time. So the time TA is the same as the time TB. So if I will cancel out the concept of time, therefore I just remain with the fact that the change in momentum of body A is equal to the minus of the change in momentum of body B. So it means that the change in momentum of A is equal and opposite to the change in momentum of B, because the time of contact is the same for both bodies. So that is what we mean by Newton's third law expressed in terms of momentum. So the examiner will ask you to explain why the rate of change, using Newton's third law, why the rate of change of momentum of why the rate of change of momentum of two bodies is equal but opposite. Number one, by Newton's third law, the force on body A is equal but opposite to the force on body B. the force on body A by body B is equal but opposite the force on body B by body A. But force is the rate of change of momentum. The time of contact is the same, and therefore the change in momentum of A is equal and opposite the change in momentum of B. As simple as that. That is Newton's third law in terms of momentum. Okay. A few things we need to note from what we have just explored here. Number one, impulse. We have said impulse is the product of force and time, or it is actually the change in momentum. Many times we define it as a product of force and time, or the change in momentum of the body, which is acted on by a constant force. And of course, because impulse is changing momentum and momentum was a vector quantity, then we can easily agree that impulse is also a vector quantity. Impulse is a vector quantity. Number three, the units. I've also talked about the units, and I said the units of impulse could either be Newton seconds because it is force times time, or they could be kilogram meters per second because it is change in momentum. Note that because impulse is equal to the change in momentum, Newton seconds will also be units for momentum. So you shouldn't get surprised when you find Newton seconds. And I think you use the same units in IGCSE. Okay. So before we advance any further, let's first do the basic examples about momentum at this level. Just remind ourselves about IGCSE momentum. A car of mass 50,000 kilograms, initially moving at a velocity of 50 meters per second, accelerates to 100 meters per second in 2 seconds. Calculate the engine force on the car that caused the velocity change. So force is the rate of change of momentum. Force is the rate of change of momentum. If you want, you can first find because this force is causing an acceleration, you can find the acceleration and use F is equal to ma. However, because I want people to get used to the fact that force is equal to the rate of change of momentum, and the change in momentum is equal to the final momentum minus the initial momentum. So it means the force is going to be equal to the mass into V minus U divided by T. But it is still the same as mass times acceleration. So the force is going to be the mass, which is 50,000, into the velocity is 100 minus 50, and the time is 2 seconds. So when you check this, this is 50,000 times 50 divided by 2. So this gives you a force of 1250,000 newtons. So that will be the force. A body of mass 5 kilograms initially moving with a velocity of 2 meters per second is acted upon by a horizontal force of 15 newtons for 2 seconds. Find the impulse and the final velocity. Of course, we know that impulse is the product of force times time. And therefore, impulse is going to be 15 newtons times 2 seconds. So the impulse is going to be 30 Newton seconds. But remember, impulse is also equal to the change in momentum. So impulse is also equal to the change in momentum. So we shall say that 30 Newton seconds is equal to the change in momentum, which is equal to the final momentum. So they gave us the initial velocity. So this is the same as mv minus mu. So this is the same as m into the final velocity minus the initial velocity, which is, or minus u. So 30 is the mass, which is 5, into the final velocity v minus the initial velocity, which is 2. So we just divide. V is going to be equal to 30 divided by 5 plus 2, which is 6 plus 2, which I think is 8. So that will be the final velocity. This is the impulse and this is the final velocity. So we have just used the concept that impulse equals to change in momentum. Here is a self-check. A car possesses 20,000 units of momentum. What would be the car's new momentum if the velocity is doubled? Remember, momentum is equal to mass times velocity. So if the velocity is doubled, it means the mass is constant. So since momentum is mass times velocity and the velocity is doubled, it means the momentum is also going to be doubled because momentum is directly proportional to the velocity. The velocity is doubled, momentum is doubled. So this would be 40,000 units. The velocity was tripled, so the momentum will be tripled. So this would be 60,000 units. The mass was doubled by adding more passengers and a greater load. So if the velocity is constant and the mass is doubled, the momentum is doubled. So this would be 40,000 units. Both velocity was doubled, both its velocity was doubled and its mass was doubled. So doubling the velocity doubles the momentum. Doubling the mass again doubles the momentum. So it means the momentum is going to be multiplied by a factor of 4. If you want to do this mathematically, you can just follow this. So let's say the first momentum is mv. The second momentum, the mass is doubled, is twice m. The velocity is doubled, is twice v. So this becomes 4 times mv. In other words, 4 times the first momentum. So the momentum here will be 4 times 20,000, which will be 80,000 units. Then determine the momentum of a 60 kilogram halfback moving eastwards 9 meters per second. Of course, we just multiply, but remember the direction is the same. 60 kilograms, 9 meters per second eastwards. So that is 60 times 9. So this is 540 Newton seconds or kilogram meters per second eastwards. 1,000 kilograms, 20 meters per second northwards. So this is simply going to be 20,000 Newton seconds northwards. Because momentum is a vector quantity, it is in the direction of the velocity. Then 40 kilograms freshman moving southward 2 meters per second. So that would be 80 meters, 80 Newton seconds southward. A golfer hits a ball of mass 45 grams at a speed of 40 meters per second. The golf club is in contact with the ball for 3 milliseconds, that is 3.0 milliseconds. Calculate the average force exerted by the club on the ball. Average force. So we know that force is equal to the rate of change of momentum. So this is of course going to be equal to the mass times the final velocity minus initial velocity divided by t. So the mass is 45 grams. A golfer hits a ball of mass 45 grams at a speed of 40 meters per second. The golfer club is in contact with the ball for 3.0 seconds. So it means, of course, the initial velocity is going to be 0. Then when it is hit, it moves at 40 meters per second. So This is simply going to be 45 times 10 to the power of minus 3. Then this will be 40 minus 0 divided by time of contact, which is 3 milliseconds. So that is 3 times 10 to the power of minus 3. To change it to seconds, because milli stands for 10 to the power of minus 3. So this will be 45 exponent minus 3 times 40 divided by 3 exponent minus 3. So the force here is going to be 600 newtons. Some tennis players can serve the ball at a speed of 55 meters per second. The tennis ball has a mass of 60 grams. In an experiment, it is determined that the ball is in contact with the racket 25 milliseconds during the serve. Calculate the average force exerted by the racket on the ball. So all we need is to find the average force from the rate of change of momentum. So they have given us the mass, so this is mass into final velocity minus initial velocity divided by t. So whether you get 0 minus v or 0 minus 55 or 55 minus v, it doesn't matter. You just need to change in velocity. So this is going to be 60 times 10 to the power of minus 3 to change it to kilograms. 55 minus 0 divided by 25 times 10 to the power of minus 3. So just check if the answer is correct. 60 exponent minus 3 times 55 divided by 25 exponent minus 3. So this gives us 132 newtons, which is 130 to two significant figures. A car of mass 1000 kilograms traveling at a velocity of 10 meters per second accelerates for 15 seconds, reaching a velocity of 24 meters per second. Calculate the change in the momentum of the car in the 15 seconds period. Change in momentum. So the change in momentum is equal to the mass times the difference in the velocities. So this is simply going to be 1000 into the difference in velocities, which is 24 minus 10. So which is, I think, 14 times 1000, that is 14,000 Newton seconds or kilogram meters per second. Then the average force acting on the car. Of course, the force is equal to the change in momentum divided by t. So it will be 14,000 divided by the time, which is 15. And I think it gives you that. Water pouring from a broken pipe lands on a flat roof. The water is moving at 5 meters per second when it strikes the roof. The water hits the roof at a rate of 10 kilograms per second. That is 10 kilograms in 1 second. Calculate the force of the water hitting the roof. Assume that the water does not bounce as it hits the roof. If it did bounce, would your answer be greater or smaller? So if it doesn't bounce, then it means force, remember, is the rate of change of momentum. Force is the rate of change of momentum, which will be mass into v minus u over t. If it didn't bounce, one of these velocities is going to be 0. So I'll just say v is 0, but I just want the change in velocity, so I can still say u minus v. So this is going to be the mass, remember, m over t times change in velocity. They have given us m over t as 10, so this is going to be 10. Change in velocity is going to be 5 minus 0 or 0 minus 5, whichever. So that is times 5, which gives us 50 newtons. So if it did bounce, would your answer be greater? If it bounces, then it means the change in velocity is going to be let's say 55.0 minus negative, because if it bounces, the velocity is going to be greater. The change in velocity is going to be greater because if it bounces, it moves in the opposite direction. So I would say 5 minus negative. One velocity has to be negative if it is in the opposite direction. So I'll say 5 minus negative. So if it has, maybe it bounces with a negative 2, it means the change in velocity is going to be 7. So I will say 10 times 7. That means the change in momentum is going to be greater. So bouncing, greater force because of greater change in momentum. So there will be a greater change in momentum because if it bounces, one of the velocities is going to be negative, and when you subtract the negative, it becomes a bigger value because this becomes plus. So if it bounces, there will be a greater change in momentum, and therefore the force will be greater. A force of 10 newtons acts for 20 seconds on an object of mass 50 kilograms, which is initial at rest. That means initial velocity is 0. Calculate the change in momentum. So we have already seen that change in momentum is the same as impulse. So change in momentum is the same as impulse, which is the same as force times t. So we have 10 newtons times 20 seconds, which is going to be 200 newton seconds. The velocity of the object at 20 seconds, that is the final velocity. So impulse is equal to change in momentum, which will be m times final velocity minus initial velocity. So I'll say 200 newtons equals to the mass, which is 50. Final velocity is not known. Initial velocity was 0 because it started from rest. So it means V is simply going to be 200 divided by 50, which is 4 meters per second. Okay, so that is, I think this is the solution. This is correct. 200 Newton seconds is the change in the momentum, and the velocity is 4 meters per second. Let's now talk about conservation of momentum. So those examples I've given are actually IGCSE examples. That just to remind you of the concepts you were supposed or you must have studied in IGCSE. So let's now talk about conservation of momentum. You also talked about conservation of momentum in IGCSE, I think, especially if you did triple physics, triple science, not coordinated science. So remember that Newton's third law leads to conservation of momentum because we saw that the change in momentum of body A was equal but opposite to the change in momentum of body B. This was if there was no resultant force acting on the system. And such a system on which no resultant force is acting, we shall later on call it an isolated system. So if the first particle exerts a force on the second particle, by Newton's third law, the second particle must exert a force, negative F, that is equal but opposite. And the minus sign indicates that the forces are in opposite directions. That is in accordance to Newton's third law. If body A is in contact with the body B, we expect that body A exerts a force on body B, and the body B is expected to exert an equal but opposite force on body A. And we saw that the time of contact was the same, and since force is the rate of change of momentum, we saw that the change in momentum of body A was equal but opposite to the change in momentum of body B, which appears as if the net force is constant, if there is no resultant force on the bodies or on the system, the momentum is conserved. So this leads to to what we call conservation of momentum. So if we express the law of momentum, if we express the law in terms of momentum, the change of momentum of the second particle as a result of the force exerted on it by the first is equal and opposite to the change in momentum or to the change of momentum of the first particle as a result of the force exerted on it by the second particle. That was Newton's third law expressed in terms of particles. Thus, the changes of momentum of the individual particles cancel out, and the momentum of the system of two particles remains constant. So the total momentum remains constant because the changes would cancel out. So the particles have merely exchanged some momentum in this case because the changes are cancelling out. So the total momentum has remained the same because the differences are equal but opposite. So this situation could be expressed as a simple equation that if the initial total momentum was p, the final momentum will be the sum of the two momentum and it will still be the same as p. So where p would be the total momentum and P1 and P2 are going to be the individual momenta of these two bodies. So the sum total momentum before should be the same as total momentum after. Therefore, the total momentum remains constant, and this is going to be called the principle of conservation of momentum. So if the system is being acted upon by no resultant force is acting on the system, then we are going to say that total momentum of the system is always going to remain constant. And such a system is later on going to be called isolated. So for examination purposes, how do we state the principle of conservation of momentum? So if no external dissipative forces act on a system of interacting bodies, the total linear momentum of the system remains constant. That is the easiest way to state the principle of conservation of momentum. If no external dissipative forces act on a system of interacting bodies, the total linear momentum of the system remains constant. Many students say conserved, which is not always credited, so we say it remains constant. Or simply, we would simply state this as the total linear momentum of a system of interacting bodies on which no external force acts remains constant. Here we must have a system of interacting bodies. We can't have one body. You can't say the total momentum of the body remains constant. We must have a system of interacting bodies because one body must exert a force on another body so that the other body also exerts an equal but opposite force on the first body. So we must have a system of interacting bodies. So the total linear momentum of a system of interacting bodies on which no external force acts remains constant. Or you can simply say that the total momentum of an isolated system of interacting bodies is always constant. When I say isolated system, it means there is no external forces acting. There is no resultant force acting on the system. So that is called an isolated or a closed system. So I want you to note that when I talk about a closed system or an isolated system, it is a system on which no external force is acting. So that is called isolated. So many times my students prefer to state the last statement because it's the easiest and the shortest. The total momentum of an isolated system of interacting bodies is always constant. Do not forget and say it is conserved. So that is the principle of conservation of momentum. And this principle of conservation of momentum is going to be very important for the remaining part of this topic. Okay, so having known the principle of conservation of momentum, let's now talk about the collisions because the collisions are the gist of the topic called dynamics. Let's talk about collisions. So to understand collisions, we are going to consider two masses on because remember this is linear momentum, we are going to consider collisions in a straight line. So a collision is in one plane, not in more than one plane. So let's consider two masses, m1 and m2, which are maybe moving towards each other with the velocities u1 and u2 respectively. So before collision, they are moving towards each other. And after collision, I have showed the time during collision. Of course, that time is very, very small. And I've shown after collision, they move apart. In our daily lives, we witness collisions without really thinking about them. In some collisions, objects collide and stick together so that they travel together after impact. They travel together as a common body or as a single body or a combined body. For example, collisions between an arrow and a target. In other collisions, like that between a tennis ball and a racket, the objects collide and bounce so that they move away with two different velocities. So in some collisions, they stick together on impact. In some collisions, they separate after impact. So let's consider this situation here where two particles collide as shown in this diagram. And in this case, we are saying after the collision, they move away from each other. Let's say they bounce off each other and move in opposite directions. Remember, or do not forget that the velocity is a vector quantity. And as velocity is a vector quantity, we are going to assign many times velocities to the right positive and velocities to the left negative. Many times students prefer to assign velocities to the right positive, velocities to the right negative. So even after collision, velocities to the left are negative, velocities to the right are positive. By the way, the reverse would also give you the same thing. You could also assign velocities to the right negative and velocities to the left positive, but it is easier for students to assign right positive and to the left negative. So total momentum before they were colliding, remember momentum is a vector quantity, that's why we need to assign the velocities these signs. So total momentum before colliding, momentum remember is mass times velocity. So before colliding we have m1 times u1 to the right and m2 times u2 to the left. So it is because we are finding the total sum. So I have to add the momentum before collision plus the momentum after collision. But the momentum after collision is to the left. That's why I have a minus here. And therefore, and also total momentum after collision. So for M1, it is to the left-hand side. So it is going to be M1 V1. But because it's to the left-hand side, there's a minus. For M2, it is to the right-hand side and the velocity is positive. So this will be M2 V2. A lot of times students forget to consider these directions when they are finding the total momentum. So total momentum after collision will be negative m1 v1 plus m2 v2. The plus here is because we are summing up. We are finding the total. So if momentum is conserved, remember total momentum before collision is always equal to the total momentum after collision if the system is isolated. So I'll just equate the two equations. m1 u1 minus m2 u2 should be equal to negative m1 v1 plus m2 v2. Or I would simply say P1 plus P2, assuming that P1 was the momentum of M1 and P2 was the momentum of P2 before, should be called P1 plus P2 after. But of course, P1 is positive, P2 was negative. Then P1 was negative after collision and P2 was positive, where P is going to be the momentum. So this is what we call applying the principle of conservation of momentum. Let's understand this in more details even. So when an object rebounds or bounces back after the collision, the velocity after the collision must have an opposite sign since the momentum changes direction. That is very, very, very important. So if, for example, here, before collision, the mass is moving towards, say, this is a wall. So the momentum, the velocity here to the right side is positive before it rebounds. So the momentum here is going to be m times u, and this is positive. But after colliding with the wall, we are seeing that the mass bounces off or rebounds. So the velocity is now in the opposite direction. So the momentum here is going to be negative m times u. In that case, if I try to find the total momentum for the same mass, it is going to be it is going to be if I try to find total momentum here, it is going to be 0, of course. But if I try to find the change in momentum, the change in momentum for the ball, of course, towards the left it will be mu minus, because change we subtract. Towards the right it was positive, towards the left is negative, so it is minus mu, and this will become twice mu. That will be the change in momentum. So when objects rebound or bounce back after a collision, the velocity after the collision must have an opposite sign. This is what students normally forget in calculations. So if there is a change in direction, the velocity must have an opposite sign. And if there is an elastic collision, we are going to understand what we mean by elastic collision. The initial and final velocities will have the same magnitude but opposite directions as shown here. So the collision, if the collision is elastic, the velocity has just changed the sign because of rebounding, but is still u, but in opposite direction. So it must be it must have the same magnitude, but just opposite, but in opposite directions. So it means if I wanted to find a change in momentum in that case, then I would say change in momentum is the final momentum minus the initial momentum, or the initial momentum minus the final momentum after I just want a change in momentum. So in that case, the change in momentum would be equal to 2mu. But I want you to note also that if I start with the other first one, I would say negative mu minus mu, because mu was positive first and that is negative, so this will give us negative twice mu. So it means the change in momentum can also be negative twice mu, because the negative indicates that the final momentum was in the opposite direction, or the change in momentum. Remember, change in momentum is always in the direction of the velocity. So the velocity changes to the left, so the change in momentum should also be to the left, because momentum is a vector quantity. I hope we understand this, especially when it comes to calculations many times. Whenever a body bounces, rebounds, or bounces back, recoils, it means the velocity after that recoil, after that rebound, after that bounce must have an opposite sign. And if you're finding a change, remember to add the opposite sign. Okay, I've given several trial examples for us, but most of them relate to IGCSE, so I'll try to go through them very fast. Two trolleys of mass 80 kilograms and 5 kilograms are traveling on the same track with the speeds 4 meters per second and 2 meters per second respectively in the same direction. So they are moving in the same direction. Let's say they are all moving to the right hand side. So all the velocities, all the speeds are going to be positive. They collide and move together. So that means they move together as a common object. So it means they have a common velocity. I'll call this one V. Capture the common velocity after the collision. Even though I don't always want to sketch this, I'll just sketch this. So initially we have two masses moving in the same direction. That is before. After collision, it becomes one body. And they will move together with the same velocity. So I don't know the direction of the velocity. I'll just put there the letter V. So these are on moving on a straight in one dimension. So after collision, of course, here the total mass is going to be 8 plus 5. So by conservation of momentum, total momentum before the collision, remember momentum is mass times velocity. Total momentum before collision is going to be the momentum, because they are in the same direction, the velocities are both positive. So for 80 kilograms, the momentum is going to be 8 times its velocity, which is 4, plus 5 times its velocity, which is 2. That is total momentum before collision. Should be total momentum after collision. It becomes one body whose mass is 8 plus 5. Then it moves with the common velocity v. So 8 times 4 plus 10 divided by 8 plus 5. So this is giving me v as 3.2. meters per second. And since v is positive, it must be to the right hand side. Because if it was negative, since I've said velocities to the right are positive, if v was to be negative, it would be to the left hand side. A 1,400 kilogram car moving westwards with a velocity of 15 meters per second collides with an electric pole and is brought to a rest in 0.30 seconds. So the final velocity is 0. Find the magnitude of the force exerted on the car during the collision. So force is equal to the rate of change of momentum. And the change in momentum is mass times final velocity minus initial velocity over t, or change in velocity to be specific. So the mass is going to be 1,400. The change in velocity is 15 minus 0, or 0 minus 15. I can say 0 minus 15. After all, this force is causing a deceleration. So this is going to be divided by time, which is 0.3. So 1400 times 15 divided by 0.3. So this is, of course, 70,000. So this answer is automatically correct. An ice skate of mass 80 kilograms, initial at rest, that means initial velocity is 0, pushes his partner of mass 65 kilograms away from him so that she moves with an initial speed of 1.5 meters per second. What is the initial speed of the first skate after this maneuver? So initially, both of them are at rest. So it means total momentum before this reaction is 0. Then total momentum after 80 kilograms. Let the mass of that first skater be 80 kilograms, and we don't know his velocity. Let their velocity be v. So an ice skate of mass 80 kilograms initial at rest pushes his partner of mass 65 kilograms away from him so that she moves with an initial speed of 1.5 meters per second. What is the initial speed of the first skater after the collision? So let's say 0 is equal to 80v plus, the other one is going to be 65 times the speed of 1.5, because the partner moves at a speed of 1.5. So total momentum after is going to be 80 times v plus 6.65 times 1.5. So I'm making v the subject. Of course, here v is going to be a negative. A negative, which means it moves in the opposite direction to the first one. So this is going to be 65 times 1.5 divided by 80. So this is 1.2, negative 1.2 meters per second. The negative is because the negative is just indicating that this one, the first skater must move in the opposite direction to the partner. So this is negative 1.2 meters per second. A cannon of mass 1.5 times 10 to the power of 3 kilograms fires a cannonball of mass 5 kilograms. The speed with which the ball leaves the cannon is 70 meters per second relative to the earth. What is the initial speed of recoil? Recoil, that is rebound. What is the initial speed of recoil of the cannon? So by conservation of momentum, the cannon of mass fires. So it means it was initial at rest before firing. So by conservation of momentum, remember momentum is mass times velocity. Total momentum before firing is 0 because it was at rest. Then after firing, momentum of the cannon is going to be the mass of the cannon, which is 1.5 times 10 to the power of 3 times its velocity. The speed with which the ball leaves the cannon is 70 meters per second. So we don't know the velocity of recoil. I'll call this v plus. For the ball, its mass is 5 times its recoil velocity, which is 70 meters per second. So because this is a recoil, we expect the velocity to be negative. In other words, it moves in the opposite direction to that of the ball. So V is going to be equal to 5 times 70 divided by 1.5 times 10 to the power of 3. So this is going to be 5 times 70 divided by 1.5 exponent 3. So the speed is going to be negative. I'm saying this is a negative because when you take 5 times 10 to the power of 70 on one side is negative. So it's negative 0.23 meters per second. The negative is correspond to a recoil. When you fire a ball, we expect the cannon to move backwards. So the velocity of the cannon must be in the opposite direction to that of the ball. So that is negative 0.23 meters per second. Before firing, total momentum is 0. Nothing is moving. After firing, we expect the cannon to move backwards as the ball moves forward. That's why the V is going to be negative. Okay. A ball of mass 0.4 kilograms is thrown to a wall. It strikes the wall with a speed of 1.5 meters per second perpendicular to the wall and bounces off the wall with a speed of 1.8 or 2. So that means this speed is going to be negative because it bounces off. So the two speeds cannot be in the same direction. Explain the changes in momentum and energy which happen in the collisions between the ball and the wall. Give numerical values. So let's first find the change in momentum. The change in momentum is going to be mass times the change in velocity. So this is going to be 0.4 into 1.5 is towards the wall minus negative 1.2. The negative here, because we are finding a change, we subtract. But because it bounces, the other one is also negative. So this gives us a change of 0.4 times 2.7. So the change in momentum is 1.08 Newton seconds. So explain the change in momentum and the energy which happen in the collisions between the ball and the wall. You can also find the change in energy, especially if it is kinetic energy, but I will not calculate the energy in this case. But of course, the energy changes which occur would be the kinetic energy is going to be converted by the impact to other forms such as heat, sound, and light, or it permanently distorts the body, leaving them with an increased amount of potential energy rather than kinetic energy. So when two or more bodies collide, their total momentum must be conserved unless there is a net resultant force acting on them. So that means the change in momentum for the ball is 1.08 Newton seconds for the ball, if I consider the ball alone. But if I consider the total momentum of the ball before collision and total momentum of the ball after collision, and then I subtract, or if I consider the total momentum of the ball and the wall before collision and total momentum of the ball and the wall after collision, of course the momentum must be conserved. If I consider the ball and the wall as an isolated system, but if I consider the ball alone, there's a change in momentum. If I consider the ball and the wall, there's no change in momentum in both cases. So I want you to note very carefully that whenever two or more bodies collide, their total momentum is conserved unless there is a net resultant force acting on them. However, total kinetic energy usually decreases, it doesn't increase. Normally, total kinetic energy doesn't increase unless there's another force which adds energy, which adds speed to the body. But normally, normally we have dissipative forces which cause the body to lose some of its energy. So this means kinetic energy usually decreases, and we shall later on call that such collisions inelastic. So this is because some of the kinetic energy is converted to other forms such as heat, sound, light on impact, or some of the kinetic energy permanently distorts the bodies, leaving them with an increased amount of potential energy or with an increased amount of stored potential energy. Remember, potential energy is the energy stored by a body by virtue of its state or position. So whenever there's a collision, we expect that the kinetic energy is most likely going to decrease, but the momentum will always be conserved. Total momentum for an isolated system will always be conserved. Okay, so I think let lesson 3 stop here and see you in lesson 4. Bye bye.